Hello and welcome to Short Text 331. In this video, we're going to talk about the inner product, also known as the scalar product or the dot product. And in fact, I would refer to it as the inner product or the scalar product or the dot product, depending on nothing in particular. So if you have a vector space, what we call an inner product is something very simple. It's an operation between two vectors that gives you a number. So you have two vectors, we're going to call them here v and w, and there's this operation we call an inner product, and as a result, when you do that operation on the two vectors, you get a scalar. So a number s here in the set big S of our scalars, and v and w are of course vectors in v. And the notation here varies quite a bit. You will find many books on functional analysis, for example, if you're into more advanced topics, or if you get to that point, that use simply this parentheses, comma type notation for the inner product. Is much more common for physicists to use v dot w like here, and that's typical in mechanics or electrodynamics. But you will also find this type of notation, the bracket notation, which is of course typical in quantum mechanics. Now, to really have an inner product, what you need is a few properties. Okay, it's not just any operation between two vectors that gives you a number that gives you a scalar product. So for you to have a properly defined scalar product, you need these three properties. The first one is called the conjugate property, which is very simple. It just says that if you calculate v with w, the inner product of v with w, and then you flip w with v, you flip the entries, then you get the complex conjugate of the previous result. So v dotted with w is w with v complex conjugate. This is a property that's really only important if your space involves complex numbers. That is the case typically in quantum mechanics, but not always. And typically when you deal with vectors in electrodynamics or in mechanics, this doesn't play any role. But keep in mind that this is important then if your vector space involves complex numbers. The next property actually has two parts. It's called linearity, and it simply says that if you have in your first entry here to the inner product a number multiplying your vector, then that number can come out of the inner product as it is, and x here is the scalar. And the second part is that if you have a sum of two vectors in your first entry, then you can separate the inner product as a sum of two inner products. So here you have u plus v with w, then it's u with w plus v with w, and so you can calculate this operation in two steps if you want. So these two properties together are what we call linearity. It makes sense that they're called linearity together, and it's one of the most fundamental properties of the inner product. And finally, a property that's a little different from stuff we've seen so far is the property called positive definiteness. And maybe this should be called positive semi-definiteness, but we'll just call it positive definiteness, or sometimes we'll just call it positivity, just to be brief. But all this property says is that if you take the inner product of a vector with itself, then you get a number that is greater or equal to 0. The inner product of a vector with itself is a number that is greater or equal to 0. And this is going to be very important, and you'll see why when applying or we're using this inner product. And the extra condition that comes with this is that if it so happens that this bound is saturated, so if v with v is actually equal to 0, then that implies necessarily that our v is 0. So the 0 is the null element under the sum in your vector space. So again, this product is always going to be greater or equal to 0, but if it happens to be 0, then it must be that v is necessarily the 0 vector. In other words, this product can only be 0 if your vector is the 0 vector. And other than that, we have a lot of freedom to define this operation. And once we have it, we obtain what we call an inner product space. Okay, so in other words, a vector space armed with an inner product is an inner product space. That's it. That's all you need to know for defining an inner product space. And this is very important in quantum mechanics. In particular, the spaces involved are inner product spaces. And so all these properties of inner product are satisfied. And in fact, right off the bat, when you start working with quantum mechanics, you define such an inner product. But that's a different topic. So at this point, I want to say that this series is made for my students in my Physics 331 class at the University of North Carolina at Chapel Hill. And if you find these videos helpful, whether you're in the class or not, please consider liking and subscribing. It would help the channel. And finally, if you're not in my class, or if you're not, in fact, at UNC at all, then and if you're looking for a tutor in physics or math in English or in Spanish, then I'm happy to help you. Just contact me at shorttakes331@gmail.com, or you can leave a message in the comments section below. So let me give you some examples now of these inner products. So here's an example in R3, which is an example you're very familiar with if you've ever worked a little bit with vectors in mechanics or in kinematics. So here's a vector v that has 3 components because it's in R3, and another one w has 3 components, w1, w2, w3. And here we may define the inner product as the dot product that you know and love from just regular vectors. And we define v with w, the inner product of v with w, as v1 w1 plus v2 w2 plus v3 w3. And it's pretty obvious that the conjugate property is satisfied because these are all real numbers, so there's no conjugation at all. So v with w is the same as w with v. And of course, each of these products here is interchangeable, and so there's no issue there at all. You get the same answer if you do v with w or w with v. It's linear. So linearity is satisfied. That's also easy to see. If there was an x multiplying here the vector v, then the x would be in front of each of these terms and it would be fine as far as multiplying by a constant. And also if v were made out of 2 vectors, v1 plus v2 say, or u and z or something like that, then of course these components would also separate in the same way. You could apply the distributive property and you would see right away that the inner product with the sum of 2 vectors is equal to the sum of the 2 inner products separately, and so that would work. What about positivity? That's the last property. Well, that's also very simple to check, that according to this definition, an inner product of a vector with itself is simply v1 squared plus v2 squared plus v3 squared. So it's the sum of squares is always positive. These components are always all real. And it can only be 0 if all 3 components are 0, in which case our vector is a 0 vector. And so that works out as well. And so we have a well-defined inner product. Of course, we already knew that. That's a classic example of an inner product. But it's nice to check and to see that it satisfies all the properties. A more interesting example that's very important in physics is to consider what happens when the space in question is generated by functions. And here we're considering real linear combinations of these functions. So these are what we call monomials. And imagine then that we have all possible linear combinations of these objects considered as vectors. All right. So we can see that these objects are all linearly independent. They span a vector space by definition, because any vector space that is a linear combination of these. Any vector that is a linear combination of these function is in our vector space, and so by definition, then we span the vector space. Then we have a basis, and clearly this is a basis. And in this case, the interpretation of this basis is that every vector in our vector space can be written as a linear combination like this, from I equal to 0 to n of ci vi is obviously the set of all possible polynomials, as we can see here, of degree up to n. Okay, so the interpretation is that a vector in our vector space is a function f of x, and this sum representing here the linear combination of our basis vectors is simply a sum with coefficients of monomials, so x to some power. And x could take any value from minus infinity to infinity. At least that's how we're defining it. We could have restricted this minus infinity to infinity to be a to b for any a and b, in fact. But I chose here minus infinity to infinity for the sake of this example. But you see here then that we have a set of polynomials of degree up to n. It's a very simple space. And in this space of polynomials, we can define our inner product to be the integral from minus infinity to infinity of f of x times g of x. So this is a product of 2 polynomials, and another factor, e to the minus x squared. And this factor is very important because a product of 2 polynomials will diverge to plus or minus infinity when you go to x large enough. Okay, so as you make x very large positive or very large negative, a product of 2 polynomials is going to give you another polynomial, and it's going to blow up in some direction to positive infinity or to negative infinity. In other words, if I just had this without this factor, then the integral would not converge. But with this factor, I'm sure that the integral will converge. So this Gaussian decay will help me make the integral converge. It will always overpower any power of any polynomial as long as n is finite. And so this always converges as long as n is finite, like I said. And you can check that it satisfies all the properties of the scalar product definition. We can see very easily that, for example, if I do f with f, then I have f squared, which is positive. This is positive, so the integral is always positive, unless f is 0, in which case the integral is exactly 0. So we can see right away that positivity, this property we described here and before, is actually satisfied. We can see linearity, which is inherited from linearity of the integral. And conjugate property is satisfied because we're using simply real coefficients, and so everything here is real, and we don't have to worry about complex numbers. We could have defined this inner product differently. We could have said, oh, okay, let's do something else. Suppose our space is defined with x going from 0 to infinity. So then we could have defined the dot product of f with g as the integral from 0 to infinity, f of x, g of x, and a decaying exponential. Okay, a decaying exponential will always overpower a polynomial as well. And so you would be just fine if you took this decaying polynomial, this decaying exponential, to make this product of two polynomials converge, and this integral would be finite, and again we would satisfy all the properties of the inner product. So you see we have here a case where you can have several different definitions of an inner product. We could have also defined f of g to be, f and g, the dot product, to be the integral between minus infinity to infinity of f of x, g of x, and 1 over 1 plus x to the 2n. So this power of 2n will help us make this integral converge. And in fact, it should say 2n, at least plus 1 here. This x to the 2n would not do the whole trick. Why? We'll see that if I have two polynomials of degree n here and I multiply them by one another, then I have a polynomial of degree 2n. And so at infinity, it will either go to plus 1 or minus 1, and that integral would actually not converge. So I need here at least a 2n plus 1 at the very least. And to be sure that there are no issues, I could say 2n plus 2, and then it's a nice and even function that's always positive. In fact, any weight function such that this integral converges is allowed and yields a good inner product. Okay, the function has to be greater than 0, so we have no issues with positivity of the inner product. So what's the use of having an inner product in a vector space and therefore having an inner product space? So there are a number of things that start to make sense if you define an inner product in your vector space. First of all, the idea of orthogonality, which we did not have before. Remember, when talking about a vector space, just a vector space, we have an idea of linear independence, but not orthogonality. Orthogonality comes only after you define an inner product. And we say, by definition, that v and w, two vectors in our vector space, are orthogonal if and only if v with w, the inner product, is 0. And so now it makes sense. Now, this inner product could vary. We may have different kinds of inner products, and so what this means will vary according to your definition of your inner product. But at least if you have one, then orthogonality makes sense. We could also talk about the magnitude of a vector. We could define, as we know, the magnitude as a square root of a vector with itself, which in R3 is the definition that we know. It's v1 squared plus v2 squared plus v3 square root, and that's the magnitude of the vector v. But in a space of functions, this acquires an interesting dimension in a way, conceptual dimension, I mean, and that you may have an inner product that looks like the integral between a and b, f of x, g of x, w of x, and this is going to be a positive quantity if you have f with f. So here I should have said f with f. So everything is nice and positive, and then you take the square root, and so then you would have the magnitude of the vector f. This would be the magnitude of a function, and not the magnitude in the sense of the absolute value of the function, which you can plot as a function of x. This means the magnitude as a full vector. There's one number associated with that, and so now it makes sense to talk about that. And we'll see that's interesting. That gives us a sense of distance, and we'll see that in a minute. So we can talk also about projection. It makes sense to talk about the projection, the how much of one vector points in the direction of the other one. So you see this geometric interpretation of how much of w points in the direction of v makes sense, and it's characterized by this v dotted with w divided by v with w. Now, I haven't proven that this is between -1 and 1 in magnitude. So the inner product of this normalized vector with this other normalized vector is between -1 and 1. We will show that, but but it gives us a sense of projection. So we gain by defining this inner product multiple geometrical interpretations of these vectors. And here's the notion of distance that I was referring to before. If you calculate the inner product of v minus w with v minus w is a vector with itself, and so it's positive, and so I can take the square root, and that gives me a number that's, again, I'm assuming this is the positive square root, of course, and this is a number that's greater or equal to 0, and it determines the distance between v and w. And when v is equal to w, the distance is 0, of course, and this is the interpretation. If this is v, this is w, you know that w plus v minus w gives you v, and so this is the triangle type, or sometimes called the polygon way of adding vectors. This plus this gives you v. The point here being that this difference then can be characterized as the distance between two vectors. And imagine doing that not just with conventional vectors, but with functions. Imagine then you have a difference between two functions and you calculate the corresponding integral. It's a positive number, so now you have a sense of how different these functions are in an overall global sense. Finally, I should say that I wanted to prove that this inner product divided by the magnitude of the vectors is between -1 and 1, and that's called the Cauchy-Schwarz inequality. So another way of writing it is that the magnitude of the inner product between v and w is less or equal than the product of the magnitudes. And usually when you're working with conventional vectors, you see that the dot product between two vectors is equal to the magnitude, the product of the magnitude of the vectors times the cosine of the angle between them. Now, how do we define that more generally? Well, we just define that with an inner product of our choice. But no matter how you define it, this property is always true. So this magnitude is that we usually equate to magnitude times the cosine will give us necessarily the notion that these two magnitudes, when taking the product, are greater than this magnitude of this inner product. Then this also holds true in general when we don't have an obvious sense of what we mean by an angle. So this, if you want, could be used to define such an angle, because we have, or a cosine of the angle, because we have this quantity that goes between -1 and 1. But let's prove that that's true, which again assume is the same as this Cauchy-Schwarz inequality. And to do that, it's actually very simple. If you use a smart linear combination of your vectors v and w. If you don't use a smart combination, it could take a lot of algebra, but it really is very simple if you do it this way. Consider then that we take our vector v and we multiply by this constant, which is the magnitude of w, and we subtract w now multiplied by the magnitude of v, and we're going to call that our vector x. Okay. Now we know that x with x is greater or equal to 0 by definition of our inner product, and we can go ahead and take x with x, which is greater or equal to 0, and expand it. And what you get is you're going to get this guy times this guy, and this guy times itself, and this guy times itself as well, and so on and so forth. And when you carry out all those algebraic operations, you find that you get twice the magnitude squared of v times the magnitude squared of w minus twice the product of the magnitudes, and then the inner product here of v with w. You can simplify that very easily by dividing by 2 and dividing by the magnitude of v and the magnitude of w. All those are positive quantities, so they don't alter the inequality at all. And then once you do that, you end up with this inequality, which proves that v with w, or rather the magnitude of v times the magnitude of w, is greater or equal than the inner product of v with w. Now, that proves part of the inequality. Let's go back up. That proves the part where this product is on the right here. Now, what about the other one? What about the fact that v dotted with w is greater or equal than the magnitude of v with w with the minus sign in front? So can we prove that? Yes, it's the same type of proof, but now you have to use a plus sign for your smart linear combination, and let's call that vector w, and I'm sorry, y. Let's call it vector y, and so the inner product of y with y is greater or equal to 0. And then if you go ahead and carry out the same type of operation, you will obtain a very similar inequality, but with a plus sign. And so you put that, you can put this on the other side of the equation, and that shows what we wanted to prove. Okay, that shows that indeed the magnitude of the inner product of v with w is always less or equal than the product of the magnitudes of v with w. Good. Finally, we also have something called the triangle inequality. That's also not difficult to prove using the Schwarz inequality. And it simply says that the magnitude of v plus w is less or equal than the magnitude of v plus the magnitude of w. And that's simply geometrically the idea that if you have a vector v and you add another vector w and we obtain v plus w, then this distance crossed by v plus w, which is the magnitude of v plus w, is always going to be less than summing those two distances. This is very nice, very interesting. It allows us, again, a new geometrical interpretation of vectors that we can discuss and we can use and we can take advantage of without any sense in particular of whether we're in 2D or 3D or even perhaps we may not even be using real numbers. We could just have complex numbers, and all these geometrical interpretations make sense. That's all I have for you. Please feel free to leave any comments below. As I said before, this series is meant for my students at UNC. If you find this video and this series in general helpful, please like and subscribe. It really would help the channel. And if you're not a UNC student, but you're looking for a tutor in physics and math, in English or in Spanish, please, you can contact me at shorttake331@gmail.com, or you can leave a comment in the comment section below. That's all, and until next time.